Hey everyone, welcome back to the channel. In this masterclass, we are doing a complete, from the ground up deep dive into REST API design and versioning. By the end of this video, you'll understand it well enough to use it confidently in production and explain it clearly in an interview. If that sounds good, make sure you are subscribed and let's get started. REST is one of those topics where most engineers know enough to be dangerous, but not enough to be right. We are going to fix that today, starting from first principles and working all the way through to production-grade versioning strategies. Every concept comes with real Java code and the reasoning behind the decisions. The failure mode that matters most in API design is invisible to the compiler and to your test suite. A 200 OK on a failed login, a verb-based URI like getUserByte, a versioning strategy with no migration path, these are design errors, not code errors. They compound over time, and they erode trust between teams and clients. The root cause is that REST is almost always taught as a set of conventions rather than a coherent architectural style with real constraints and reasoning behind each one. HTTP already defines a rich vocabulary of methods, status codes, and headers. When we ignore that vocabulary, we force every client to learn a proprietary dialect instead. Quick pause. If this is useful so far, drop a like, subscribe for a new masterclass every week, and share it with a teammate who would find it useful. Now, back to it. Before we touch a single line of code, let's be precise about what actually travels across the wire. Every REST interaction is an HTTP request carrying a method, a URI, headers, and optionally a body. The response carries a status code, headers, and a body. Every design decision we make today maps onto one of those elements, and each one has defined semantics we should respect. This is the pattern that triggers a reject in code review. Verbs in the URI, a GET request that deletes data, and RPC style naming that treats HTTP as a transport layer rather than an application protocol. Each of these violates REST constraints, and each one will cause real problems. Caching breaks, idempotency guarantees disappear, and client contracts become unpredictable. The corrected version uses nouns for URIs and lets HTTP methods carry the intent. Post to users creates a resource and returns to 01 created with a location header. Delete carries delete semantics and returns 204 number content. Get is safe and idempotent. Every HTTP intermediary, proxies, CDNs, API gateways understands these semantics and behaves correctly because of them. The rest of this masterclass builds on what we just established. Resource modeling teaches us how to name and structure URIs so they reflect domain concepts cleanly. Status codes form the contract between server and client, get them wrong, and every error handling path in every client breaks. And versioning is how we honor that contract over time, even as the system evolves. REST is one of the most misunderstood terms in software engineering. Most developers have been using it for years without knowing where it came from or what it actually requires. We are going to fix that right now by going back to the source. In 2000, Roy Fielding submitted his doctoral dissertation at UC Irvine. In Chapter 5, he defined an architectural style called representational state transfer (REST). What makes this historically significant is that Fielding wasn't theorizing in a vacuum. He was simultaneously helping write the HTTP 1.1 specification. REST was his attempt to capture the architectural principles that made the World Wide Web scale, so engineers could build systems that worked with those principles rather than against them. The single most important takeaway here is that REST is an architectural style, a collection of constraints. It is not a protocol you implement, and there is no standards body that certifies your API as RESTful. The moment you treat REST as a checklist of technologies, you've missed the point entirely. Understanding the constraints is what separates an HTTP API from a genuinely RESTful system. Fielding defined 6 architectural constraints. Violate any of the first 5 mandatory ones, and, by strict definition, your system is not REST. The uniform interface constraint is the most central. It breaks down further into 4 subconstraints of its own, including HTOAs, which we will cover in depth later. Keep this structure in mind as we walk through each one. The first 3 constraints establish the foundation. Client-server separation means you can evolve your front-end and back-end independently. Statelessness is the one developers get wrong most often. A JWT token traveling with every request is not a violation, it is the state carried by the client. Because no server instance remembers anything between requests, you can add instances freely. Cacheability then builds on statelessness. A GET endpoint with no side effects can be safely cached by a CDN, dramatically reducing load. The uniform interface is the constraint that makes REST REST. Its 4 sub-constraints work together. URI names the resource, a representation carries its current state, headers and status codes make messages self-describing, and HTOAs means the server tells the client what actions are available next rather than the client hard-coding that knowledge. HTOAs is the sub-constraint almost nobody implements correctly, and we will dedicate significant time to it. A layered system means you can insert load balancers, API gateways, and caching proxies transparently. Clients never need to change. Code on demand is the only optional constraint. Sending JavaScript to a browser is its canonical example. Now for the pragmatic reality, most production APIs violate at least one of these constraints, and that is acceptable. The goal is not religious purity. The goal is understanding why each constraint exists, so that when you do break one, you do it deliberately and you fully understand the consequences you are accepting. Leonard Richardson's maturity model gives us a precise vocabulary for talking about how well-designed an HTTP API actually is. Martin Fowler brought it to mainstream attention, and it remains one of the sharpest mental frameworks in API design. We are going to walk up all 4 levels and understand exactly what separates each one. Each level builds on the one below it. Level 0 is the baseline, a single endpoint used as a raw transport tunnel. Level 1 introduces separate URIs per resource. Level 2 adds correct HTTP verb semantics. Level 3 adds hypermedia controls, which is what Fielding's original REST dissertation actually requires. Most production systems sit at level 2, and that is worth knowing. Level 0 uses one URI and almost always post for every operation. The action being performed is encoded inside the request body, not expressed through the HTTP layer at all. This is SOAP, XMLRPC, and a surprisingly large number of microservice APIs written by developers who opened a REST controller without thinking about design. You could replace HTTP with raw TCP sockets, and nothing about your protocol would change. Level 1 is genuine progress. You are now modeling your problem domain in URI structure rather than burying it in a body payload. Level 2 is where most well-run engineering teams operate. Verbs carry intent, status codes carry outcome, and URIs identify resources. Fielding himself wrote in 2008, explicitly, that level 2 APIs are not REST because they are missing level 3. That is a hard fact worth remembering when the word REST gets used loosely. Level 3 embeds hypermedia controls directly in the response. The server tells the client what state transitions are valid right now. If the order were already paid, the pay link would simply not appear. The client never needs to hardcode business rules about valid state transitions. This is HTOAs, hypermedia as the engine of application state. It is elegant and powerful, and we will dedicate a full section to when and whether you should implement it. When an interviewer or architect asks whether your API is RESTful, the strong answer is precise: state the RMM level, name the HTTP semantics you rely on, and explain the trade-off you made at level 3. Saying your API is level 2 on the Richardson maturity model, with correct verb semantics and resource-oriented URIs, and that HTOAs was a deliberate architectural decision because of client complexity, that answer signals exactly the kind of design thinking senior engineers are hired for. REST is widely used, but its core concept, the resource, is widely misunderstood. We are going to fix that now, starting with a precise definition and working through the structural rules that follow from it. A resource is not a row, not a POJO, not a function, it is a named concept. This distinction matters because it forces you to model what your system knows about, not what your system does. Everything else in REST API design flows from getting this definition right. Every one of these URIs encodes a method call. GetUser is a function, createOrder is a procedure. This is level 0 RPC thinking applied to URLs. You are expressing what you do rather than what you have. The HTTP method becomes meaningless noise because the verb is already baked into the path. The URI now identifies what we are talking about, and the HTTP method tells us what we are doing to it to separate orthogonal dimensions. Notice that get, put, and delete can all share the same path users 123, only the method changes. The resource model is the most important architectural decision you will make for your API. These 6 rules work together as a coherent system. Plural nouns, lowercase hyphenated paths, no trailing slashes, no format extensions, no verb duplication, and a controlled escape hatch for actions that genuinely do not map to CRUD. Internalize all 6 and your URI surface will be consistent and intuitive. Plural nouns reflect the fact that the collection and the individual item are distinct resources, each addressable independently. Hyphens are preferred over camel case or underscores because underscores can disappear under hyperlink formatting in some rendering environments. Trailing slash inconsistency causes silent 301 redirects and client confusion. Pick a convention and enforce it with a filter or gateway rule. Embedding .jso or .xml in a URI binds your public API surface to an implementation detail. Changing format would break every bookmark and integration. Rule 5 is the mirror of the noun principle, because HTTP already provides get, post, put, patch, and delete. Adding a delete subpath is redundant and dilutes the uniform interface. Rule 6 is the safety valve. When an action truly cannot be modeled as a state change on a resource, name the action itself as a noun and post to it. Real-world APIs constantly face operations that don't fit neatly into create, read, update, or delete. This section covers 3 proven patterns for state transitions: the nesting depth rule that prevents URI chaos, and the pagination strategies that keep large collections performant and predictable. When you need to cancel an order or process a refund, you are describing a state transition, not a data mutation. The right modeling choice depends on how much history you need to keep, how complex the domain logic is, and how much rest purity your team values. Each of the 3 patterns is legitimate. The key is consistency. Option A treats the transition itself as a resource. Posting to the cancellation subresource creates a cancellation record you can retrieve later, giving you a natural audit trail. Option B uses verb-like subresources, which is less pure but unambiguous and widely used by respected APIs. Option C patches a status field directly, which is the most common approach in practice but requires server-side validation to reject invalid state transitions. The cancellation endpoint returns 201 created with a location header pointing to the new cancellation resource, because we literally created something. Notice that business logic lives in the service layer. The controller only handles HTTP concerns. The cancellation record captures reason, timestamp, and refund status, giving you a full audit trail for free. The patch endpoint uses JSON patch, which is RFC 7396, not a custom partial update hack. Crucially, validate state transition enforces business rules after the patch is applied but before it is persisted. The API trusts the HTTP layer only as far as deserialization, domain invariants are enforced in the service, not the controller. A URI-like companies 1 departments, 2 teams, 3 members, 4 projects, 5 looks thorough but is brittle. If a project can belong to multiple teams, the entire hierarchy breaks. If you rename a department slug, every downstream URI changes. The fix is to promote deep resources to top-level endpoints and use query parameters for filtering projects. Team ID is equal to 3 is far more durable than 5 levels of path segments. The deep nesting pattern couples your URI design to a single ownership hierarchy that the real world will eventually violate. Promoting resources to top-level endpoints and using query parameters for filtering gives you stable canonical URIs, clean caching boundaries, and the flexibility to support many-to-many relationships without redesigning your entire API surface. Let's recap the key takeaways from this masterclass. If this helped you, hit the like button, subscribe for a new deep dive masterclass every week, and forward this to a teammate who would find it useful. Drop your questions in the comments. I read every one. See you in the next one.